Okay, very short lecture this. So really what we want to do is just to remind ourselves about momentum conservation and how we're going to apply force momentum to a control volume. So one of the key points is that this is very different to the Bernoulli equation, where you were using this with a streamline. Okay, so just to sort of remind ourselves, we've got scalar and vector quantities, and momentum is a vector quantity, and the thing that we're interested in is the velocity. It's momentum per unit mass. So when we write a momentum equation, effectively we're going to write three momentum equations, one for each direction. And if we just want to write one of them, we have to define the direction that we're interested in. So the x direction momentum is something like this, and the momentum vector is something that looks a bit like this. Okay, and in reality we're interested in applying Newton's second law to a control volume, and to do that we have to go through going from a Lagrangian to an Eulerian frame of reference. So just to sort of remind ourselves about control volumes, here's my surface, and I want to conserve the amount of stuff going in or out of it. So what I want to be able to say is the amount of stuff going in must equal the amount of stuff going out, and I can use that using the dot product and the surface normal. So here's my dot product. I've got two vectors, and I end up with a magnitude which is this thing. So we use this to work out the normal component. So vector A, if you like, if we've got vector A and vector B, vector A is the velocity vector, and vector B is the unit normal to this little area element. And if I work that out, I end up with the magnitude of the velocity times cos theta, or what that really is, that's the component of this velocity vector in this direction. So this is the normal component of the velocity vector normal to this face, and this defines the mass flow through this area element. So I have an elemental mass flow, and that's the density times the normal component multiplied by the area, and I can do that for any one of these area elements, and I can sum all of those up, and I can work out this integral here, and then I can say, well, conservation of mass tells me the amount of stuff flowing into the control volume must be the same as the amount of stuff flowing out at steady state if it's incompressible. So this is my conservation of mass equation. Okay, so we're going to do the same sort of thing for momentum. So we can do this quite easily. So this is our master equation, Newton's second law, and we can go from this to an Eulerian version of that using the Reynolds transport theorem, and that gets us the rate of change of momentum in the control volume plus the net rate of flow of momentum into the control volume. Okay, and we can do this for anything, but here we're going to do it for momentum. So when we want to start thinking about conserving momentum flow, we can just make use of the argument that we use with mass flow. So if you like, when we work out our mass flow, this normal component of the velocity is actually carrying density out through the control volume surface. So we can use the same approach and say we want to carry momentum out through this little elemental surface here. So this dmx, this is the amount of x momentum being carried out of the control volume in this particular direction. Okay, and this is a force that's being acted on. Okay, so when we do that, we end up with a momentum equation that looks like this, and we've done this using a control volume. We don't assume a streamline, so the Euler equation is a special case of this equation when it's applied to a streamline. In our case, these forces that we might be interested in are pressure gradients, gravity, and viscous forces, and we're not going to deal with anything clever or interesting. Okay, so for force momentum problems that we're going to be looking at, we're only going to look at steady flows, so this term will always be 0, so that gets rid of that. And most of the momentum problems that we're going to be looking at are inviscid. So that means that we can make a simplification of what the momentum is coming in through an inlet or an outlet. We can just say it's the mass flow multiplied by the velocity component that we're interested in. So that allows us to simplify this type of equation to this type of equation. So this basically says I've got a control volume. These are my momentum flowing out of my control volume. This is the momentum flowing in. The imbalance between these two is the sum of the forces on this control volume. And in our module, so what we do is we say this is true when it's inviscid, it's not near a wall, and when the Reynolds number is very, very large. And if we have one inlet and one outlet, we can make it even more simple. It's just the difference in the velocities. Okay, and this equation can be simplified when there isn't any flow at all. So all of the left-hand side is 0, and then it's the sum of the forces are equal to 0, and the two forces we've got are pressure forces and gravity forces. So all the lectures that Luke did is effectively a special case of momentum conservation with no momentum. And then the final part of the module, we look at viscous problems. And in a sense, we say that all of the left-hand side is 0, and these forces, the sum of all the forces must equal to 0, and the viscous forces are the key ones. So forces involving the viscosity of the fluid. And in essence, what that means is the Reynolds number is much, much less than 1. Okay, so we now reminded ourselves what we can do with the momentum equation. You can now complete all of the chapter 10 questions and have a go at handing in 10.9.